In the lesson video for day 8.1, we're going to be talking about simplifying radicals. And the word radicals refers to the symbol for square roots. And we've done some work with square roots before, or you have in other classes at least. And so we're going to take a look at how to simplify those without actually using the square root feature of your calculator. We're not going to get decimal answers. We're going to reduce these, what we call radical expressions, these square root expressions, into their simplest possible form. And we're going to start with something that is a little more familiar to you, and that's when we are taking the square root of something we call a perfect square. Any number that is the result of an integer squared to the second power is called a perfect square. So when I say 2 squared and I get 4, 4 is a perfect square. 3 squared equals 9, 9 is a perfect square. 4 squared is 16, 16 is a perfect square, so on and so forth. You can kind of get the idea of the pattern of those perfect square numbers. So when I do the square root of a perfect square, it goes back to this base number here, because the square root of 4 we might know is just 2. If you use your calculator, you get the square root of 4 is just 2. But what I want you to understand is it's actually rewriting 4 as the product of two identical numbers. Okay, so we're thinking of it as square root of 4 is really root 2, 2, or the square root of 2 times 2. Because when you get used to seeing the pattern of these double factors, these factors of the same base twice, that allows you to pair them up and take them out of the square root as just the individual value 2. Okay, so the same thing with the root 9. We recognize that 9 is 3 times 3. So I can rewrite 9 as product of 3 times 3, at least in my head, to understand this a little bit better. And I get that the square root of 9 is just 3 then. Because I can pair those up, the square root of them takes it down to just one of those 3's, and that's how we get that. Okay, so for the square root of 16, we would also pair that up and realize that the square root of 16 is just 4, because that 16 can be written as 4 times 4. And so when I have a pair of those 4's there, I take those out, and I just get 4. And so what the pattern is that we're recognizing is if I have the square root of two numbers that are identical to each other, multiplied together, that square root is just one of those numbers. Okay? And we could also realize this. If I have the square root of two different numbers, like an a times a b, I can take those square roots separately. Okay? And so what we're going to end up doing a lot in this lesson is actually doing some factoring. Okay, we're going to be taking some numbers, and we're going to factor them down, and we've done this in other lessons, but we're going to use our factor trees some of the time. Okay, so for the number 20, to factor 20 into its list of prime factors, we would do 2 times 10 maybe, and then we realize 2 is a prime number, so it's just going to drop down, but 10 can still be factored into another 2 and a 5. So 2 times 2 times 5 is the list of factors that make up 20. And that is going to be useful, especially when we look at our first example here, when I'm told to simplify the square root of 20. When I look at the square root of 20, and I'll show you, we just did this right here. We took 20 and we split it into its list of prime factors. So I'm going to do that. 2 times 2 times 5. I'm going to rewrite 20 as 2 times 2 times 5. Now, you might have done this a different way in another class, but I'm going to kind of show you the method I want you to follow through this, and you'll get to where you do some of this in your head mentally, but for the first few examples, it's really important to write these steps down. And so what I want us to do, as we look at this, I want you to look at grouping those two that are alike together, okay? I want you to understand that we should group those together. And in fact, we can even rewrite those as a separate radical or separate square root from that other one. Because this, the square root of 2 times 2, becomes just 2. And that leaves times the square root of 5. And usually we don't even write the times dot. We just say 2 square root of 5 is our answer. Okay? And that is simplest radical form of the square root of 20. Okay, let's try another one. Okay, let's simplify the square root of 288. Now 288 is a little bit bigger number, so we're going to start by making a factor tree there. Okay, there's a lot of ways you could go about this. Most of you are probably going to see that we can just divide by 2 first. 2 times 144 is 288. And then we're going to keep kind of going and breaking this down. That 2 is going to drop down. 144 again is going to split into another one. We can do this a couple different ways. I like to notice that 144 is a perfect square. That's 12 times 12. Okay, so this 2 drops down again. These 12s are going to split up. Maybe you notice that's 2 times 6 for the 12s. And now every one of these 2's drops down again. But the 6's split up into 2 times 3. So we've got 1, 2, 3, 4, 5 factors of 2 and 2 factors of 3. So I'm going to rewrite this a little bit longer like this. 2 times 2 times 2 times 2 times 2 times 3 times 3. And then we're going to group them up in pairs. All right, we're going to pair these up. Okay, every 2 get paired up. And that leaves one of those that's not going to pair up. That 2 there is not going to pair up the same. That's okay. So these 2's become just 2 outside of the radical. These 2's become another 2 outside of the radical. And these 3's become another 3, or just a 3 outside of the radical. The only thing left underneath the radical is this 2. Well, I can multiply all of these together now. 2 times 2 is 4. 4 times 3 is 12, leaving square root of 2 under that radical. So the square root of 288 becomes 12 square root of 2. Okay, there's one other thing I want us to look at, and that's when we introduce variables into the mix. Okay, so you might be given something like this. It might say simplify the square root of 300 x squared y. Okay, well, we're going to take a look at this, and we're really going to separate this into 3 chunks. We're going to do the square root of 300 separately from the square root of x squared and separately from the square root of y. And we're just going to treat these as 3 things being multiplied together and put them back together at the end. Well, 300, you might recognize, if we take our 300 and do our factor tree, that's 3 times 100. 3 is a prime number, so it drops down. 100 is 10 times 10, and there's a pair of numbers, so you might even see that we could stop once we get a pair, and we don't have to go back and put down to the smallest values. So this 300 really is 10 times 10 times 3. Those pair up to be a 10 outside the square root, leaving a 3 inside the square root. And then when you look at the x squared, you need to understand that x squared is x times x, and that's a pair of factors x, and we wrote that even earlier right here. Okay? So the square root of x times x is just x. So that's just x there. And then the square root of y, there can't be anything to pair up out of that, so it stays underneath the radical. So there's 2 things left under the radical. We're going to group those back together. Okay? But the other things outside the radical are the 10 and the x. So they group together outside. The 3 and the y group together inside. And that would be your final answer for that simplest radical form. Let's try one more of those examples. Let's say I gave you the square root of 50 n to the third. Okay, the square root of 50 n to the third. Well, again, we're going to split that into the square root of 50 and the square root of n to the third. The square root of 50, we are going to write our factor tree. Okay, that's 5 times 10. 10 is 2 times 5. So I could rewrite this as 5 times 5 times 2. That'll give you your pair of 5's we need. But the n to the third is n times n times n. Well, we're going to pair up 2 of those. You always have to have them in pairs of 2. So the 5's come outside the radical, leaving 2 inside the radical. The n's come outside the radical as a single factor of n, and leaves this other n underneath the radical. So this 5 and this n go together, and this 2 and this n go together. And so that's one way we can use variables in simplifying radicals as well.